Today we're going to discuss some tools and technologies as well as some areas previously that were part of AI and tools that are available today, how these have kind of evolved. Historically, um, all AI was concerned was with static systems, systems that don't change over time, and they were developed manually. Now, with the advent of new AI technologies, what's happening is that several things have moved on. Okay, previously, when AI technologies were being developed based on, let's say, software models and algorithms, people typically using AI-based systems uh, were really not pushed, and there was really no need for them to learn and know about the underlying technologies in general. So, an average person using those systems built around the AI theme, like expert systems, which were, of course, developed manually, an average person would not really be interested in the technologies working behind the scenes, right? That was the case. So they could live without it, and there really was no need. Though those technologies were essential to develop such systems, but an average person, as I said, using them really didn't need to know them. Now that new tools and technologies they have evolved so much, AI itself, okay, has become, as they call, ubiquitous. It's everywhere. It is everywhere. And with this new situation, things that were really not that directly concerned with the people using those systems, and that is no longer the case. So an average person, which really means all people in the future, now, today, and tomorrow, all of these will require to know what underlying themes, technologies are there. So they want to align, they would like to know, and they need to know how they're syncing with their needs and how they're being applied. While they are important, of course. So as a person, as a layman in AI, you really wouldn't need to know, but it becomes essential, and it is rather important that you should know the essentials of these. And as I said, as we move along, there would be hardly anyone who would be unaffected by the effect of this presence of AI everywhere, every field of life. Before coming to that, but let's just look at if what we call as the golden era of AI, previously as you used to be, the good old AI. Good old AI systems were basically static systems built around what I just mentioned, expert systems. They were kind of hard-coded, programmed solutions to people's requirements, manually programmed, right? There was no automation behind that in terms of the software improving upon itself. So if you were to give a set of inputs to one system, it would give you the same outputs. You go somewhere else, give another set of inputs, you'd get the same output, right? And if you were to change and improve upon the system, you would have to then reprogram everything. You'd have to reprogram everything from scratch again. So one of the essential reasons, the limitations of these old, AI, the static systems, is that there was a limitation. It could be very good, but there was no room for improvement except manual intervention. Anyway, we will discuss that in a while. Symbolic logic, for instance, that is another trend that has evolved. Okay, and like mathematics, so symbolic logic relies on modeling the world as a set of symbols, and then their relationships between them, and to manipulate those symbols. Okay, like mathematics is a form, uses a form of symbolic logic. When we try to understand problems, we try to conceptualize, and that conceptualization means creating mental models about the problems. And this is where we're good, where human beings are good at. Maybe we'll come up with this again. So symbolic logic and its uses. And then, of course, you need to represent that symbolic logic in some form that we come up when we discuss knowledge representation. Expert systems has been the mainstay of AI in the golden ages, or the good old AI as we call it. Basically coded into if-then rules, and by interacting with experts. Decision trees, for example. A decision tree is basically a set of comparisons, okay, applied to an input, and then based on the parameters, you will decide one way or the other. And then if you go to the next step, you want to then apply the same set of rules or conditions that are available, and come up with further growth into directions, options that you can have. So you have a baseline where you start from, and then from there you maybe want to have, you have 2 options or 3 options. So you draw symbolic lines from that baseline, and then from there move on to other aspects. And this is how a structure of a tree is kind of formed in a reverse form. Tree is upwards, but this is kind of downwards. So, but this is called a decision tree. So we may move between comparison and then decisions. For instance, let's take an example. We have, let's say, a weather situation, and we have other options. For instance, we want to decide whether we want to go out today or not. So weather is one parameter that we look at, and we also look at, let's say, what is the humidity, what is the wind situation, and so forth. But let's stick to weather and the humidity situation and the wind blowing. Now, if you look at the diagram, weather has 3 situations, 3 options, 3 conditions. Weather can be sunny, it can be cloudy, or it can be rainy. And humidity too, once again, in here we've shown 2 parameters. Humidity can be high or normal. Likewise, there could be wind blowing as well. And the wind can be strong or weak. Now let's try and build up a sequence of decisions that we can take based on this decision tree. How does it build up? So you look at weather, and then you look at the 3 options. Let's say if the weather is cloudy, for instance, you maybe want to go out for a walk or a drive. That's one of the decisions of the tree, and you can see that branch of the tree going down, saying, yes, let's go out. Next, you say that the weather is sunny. Now there you have a slight bit of decision making to do. If it's sunny, let's see how humid it is. If it is high humidity, it is sunny, but it's very highly humid, you probably say, no, I don't want to go out. If the weather is sunny and humidity is normal, you probably say, yes, let's go out. And so each of these, the links that we show are the branches that move from one node or set of the tree, partial set, and going downwards. So in a development of a reverse structure of a tree. If you look at the wind situation, in the wind situation, once again, the same thing applies. Let's say the weather is rainy and there is wind. Now you want to know, what does wind look like? Wind could be strong or weak. So if it's rainy and the wind is weak, you can say, yes, go ahead. If it's rainy and the wind is strong, you'd say, no, let's not go out. Semantic graphs, another very interesting feature. Semantic graphs are more of concerned with more modeling of information, okay, based on semantic representation. Semantic means the language thing. You say a cat is a mammal. A mammal is an animal. Something is a tree or something is a bird, and so forth. So these semantic graphs basically are used to represent semantic related information between various objects. So an important technology within the realm of AI. They describe, as I said, relationship between entities or topics and ideas, and they are structured like graphs. Now here is an example. You have animals on one side, you have mammals on the other, okay, and so there's a linkage between them. You can say an animal, okay, can be a mammal. You start with let's discuss a cat, for instance. So a cat is an animal. It is vertebrate. It has a fur, which is the coat of the, right? And then you can say, all right, there's a bear, which is also a mammal. It is also an animal, and so forth. So these semantic graphs, or semantic networks rather, they are used to represent relationships between objects. And one of the greatest use of these semantic graphs, typically available from Google, is a knowledge graph. You're trying to find out the highest peak in the world. So there's no computation behind this. Remember, there's no computation behind this if you have built a knowledge graph. So what would that have? That knowledge graph would say, all right, the highest mountain peak in the world is Mount Everest. Now, there is some representation of this in the form of this graph that I just mentioned. Okay. So all it does is it goes looking for this information is lying somewhere in that knowledge domain from where Google is trying to gather information. There's no computation as such behind this. All is the representation in a graphical format. You would have a mountain, you would have a mountain range, you would have, the higher mountains, and then somewhere they're represented, the heights they're represented. So if you were to go and just ask what is the highest mountain peak, the Google knowledge graph would simply travel on that graph and come to looking for mountain peaks, and then it will have that information in one of its branches, and it will come up with the highest mountain peak in the world. So as I said, this knowledge graph has really, when you get very quick answers from Google search, remember, part of that is a knowledge graph. Very, very powerful technique. Next is optimization. What is optimization? Optimization is trying to determine, the best route from your home to your office, right? And what is the time? So if you were to go to your office in the morning, 9 o'clock, what is the best route? And that optimization tells you that choose the following sequence of roads, and you will get to your office in time. There could be several routes to your office at 9 o'clock, but which is the best route, shortest route, right? So that is optimization used by Uber and FedEx and so forth. And then you could say, I'm not worried about time, just tell me where there is least traffic. I don't want to be bothered. So that's another optimization. Static AI, of course, I've discussed before. Static AI were those systems where they were fixed. No new information could be added rather than except simply reprogramming them. One of the most important technologies, modern technologies of the day, which have actually overwritten virtually everything, is neural networks. So what are neural networks? Neural networks are interconnected nodes, much like the brain, okay, and they process loads of information, parallel processing, and come up with several advantages which are being used today. Okay, so this is one side. The old-fashioned AI, static, was hard-coded knowledge versus things that are programmed or designed to do something, but also improve upon themselves. So the knowledge base in the expert systems had to be reprogrammed. Whereas in neural networks domain, it actually learns itself. So it is adding to its own knowledge. We'll discuss this when the details of this topic are discussed. Internet of Things, very interesting. What is Internet of Things? Internet of Things tells us that there are devices at home, in offices, buildings, cities, and they are intelligent enough to actually communicate with each other. Okay, and a common example in our domain, the gas meters, for instance, there are about 6 to 7 million. For each of them, every month somebody has to go and read from our homes. A long exercise. Now, come to think of it, if these meters were intelligent enough to actually talk to each other, if they can talk to each other, then we could build up a mesh of these. So they are communicating with each other within certain distances. So they pass on their own meter readings at a predetermined interval every month. And that is collected and brought to the gas company. Okay. So this would be one small example of what is meant by Internet of Things. And you can think of several other applications, right? So smart objects talking to each other, creating an environment where they manage information between themselves for taking intelligent decisions. And machine learning, we create a machine that can learn on its own. So if it is able to learn on itself or on its knowledge and make improved decisions or predictions or analysis or face recognition, right? The job is done. It simplifies lots of areas, and this is what's going on in machine learning. Then autonomous vehicles, okay, they're learning, they're given obstacles, okay, so they know what the rules are, how to learn, how not to touch an object, and how to make a braking system, and so forth. Agent technologies. What is agent? If you've heard about robots, they are physical machines. The software only equivalent of a robot is called an agent. A robot, of course, is a physical object. It does many things. It thinks and then it carries out those functions, right? The software only component equivalent of this robot are agents. And they're trained to carry out tasks, complex set of tasks, and divide them into smaller components and carry out those tasks. The most common of this is chatbots, and they're used everywhere. And I'm sure you're familiar with a smarter child and so forth. So robots are one typical example. Blockchain, another very interesting example. Blockchain really is a concept which is trying to create a working relationship, let's put it, between parties that don't trust each other, but they have to work together. The parties that they need, I mean, they're countries, for instance. There could be other organizations. They don't trust each other, but they're forced to carry out certain transactions between themselves. Okay? So typically called the Byzantine generals problem. The Byzantine generals, ages ago, they had to manage various tribes. They didn't trust each other. So the general had to find a communication mechanism between those tribes that did not trust each other. And that's where the concept of, that's where we take the concept of blockchain from there. Financial transactions, I said. Okay. So rules created without relying, and then they come up together to create financial transactions between untrusted parties. We'll discuss this more in detail when 90% of the European Payments Council believe that this blockchain technology will be the fundamental thing going on in the industry in about 5 years from now. Deep learning. Neural networks are the fundamental components where learning takes place. As I said, learning is one step ahead of the expert system, which was the static technology. Neural networks, they learn from experience. That's the way they are built. Deep learning is a subset of machine learning. So a high-level representation, let's say fraud detection. In fraud detection, somebody wants to, in a banking system, they want to have a fraud detection system. So what they do is they look for transactions beyond a certain amount of the currency, say US dollars or whatever. So your first level of neural network will classify each of those transactions and look for patterns, abnormal patterns in the payments beyond a certain value. Once that is obtained, deep learning will actually go to the next level and add to those financial transactions the IP address, the date, the time, right, of each of those transactions, sender, user, social media event, and whatever. So they will go deeper down with those transactions, where are they coming from, where they are going, and then pass it on to somebody else. They say, all right, where are they going and where are they coming from? What are the IP addresses? So with each additional layer of that neural network, we are going deeper down into finding out very specific cases which are potential for frauds. Augmented and virtual reality. Virtual reality is basically a new technology whereby a synthesized environment is created, and you have a headgear that you put it on. So you go around, and it is as if you are physically standing in that physical space, and you look around rooms, chairs, tables, if you're going through a room. Augmented reality is a step ahead of this. What it does is it gives you a complete view of the physical systems, and then added onto it the synthesized versions as well. So you can't differentiate in augmented reality. You can't differentiate whether this is a real object or not. So for AI, augmented reality, everything is actually real, as opposed to virtual, where you know everything was virtual, nothing was. So here you can have human beings coming in AR, whereas you're looking around, and then a person comes in as if that person is physically there, which it is not. Knowledge representation, once again, very interesting field. I discussed earlier on. Just know that human beings are very good at symbolic reasoning. So you need to have mechanisms for representing knowledge in symbolic form. Natural language processing. NLP is very, very growing, very, very interesting field. And the reason we need to know this is that, you want to communicate with the computer. So the computer needs to understand natural language and take your requirements. And of course, carry out the instructions, whatever you want to do. And then the output from the computer also has to be in the natural language format. So two-way communication. So tools and technologies, there's several tools and technologies available. The most relevant one that you need to know that we're going to use in this course is a tool called MATLAB, which provides several libraries for you to build, and we're going to use that to prepare a case study on fuzzy systems. So MATLAB. And the other one that you need to know in general, we don't intend to use that as such, is Python and its associated libraries. These are two tools. If you use Python, you have a lot more flexibility. You can build your own things as opposed to MATLAB. But then you can build faster using MATLAB. So I hope this has been interesting and useful. We'll be taking these things up further. The idea was to create a little bit of excitement. I hope that we've been able to do that. Thank you very much.